Integration by substitution, part 2. In part 2, we are going to also use the substitution rule to evaluate definite integrals. Let u be g of x, and du is g prime of x dx. So that if we have a definite integral from a to b of f of g of x, g prime of x dx, we will let g of x be u, like we always did. We're gonna pick the inner function of a composite function and call it a u, and then take the derivative each side. So we get du equal g prime of x dx. And of course, it's right here. So we are going to substitute as f of u du. Now, in indefinite integral, we would just take the integral of that, and then we had to do the back substitution. But with the definite integral, we are going to find out the upper limit and lower limit for u. So in original integral here, these limits were limits for x. You have a lower limit of x and upper limit of x variable. However, after u substitution, we are going to find out when x equal lower limit a, u, the limit for u will be, you plug that a right here so that you get g of a as a number, and that will be the lower limit for u. And then when x equal upper limit b, you can find out what would be upper limit for u, and u is g of x, so you can plug g of x equal b to get the upper limit for u. So then your integral now become ga to gb of f of u du. So there is no back substitution for definite integral because we changed not only everything in u, but you changed the limits for u as well. So now when you found the antiderivative, you can actually plug these limits for u without doing the back substitution. All right, let's go ahead and do one example. What is the integral 0 to 2 of x squared over square root of x cubed plus 1 dx? I would like to rewrite this as a product using the power. So let me rewrite this integral. This integral is equal to integral 0 to 2 x squared times x cubed plus 1 to the, since I'm bringing from denominator, it will be negative 1/2 power dx. So now I see that I have a composite function. So then let u equal inner function of my composite function, which is x cubed plus 1. Then my du will be 3x squared dx. I'm gonna come back to my integral and I see that I have x squared dx for my du. I'm just missing 3. So I'm going to multiply this integral by 3 and divide by 3 so that all I have done is multiplying this integral by quantity 1. Now I'm ready to do the substitution here. 1/3 integral, this is u to the negative 1/2 power, and 3x squared dx is equal to my du. So I'm gonna have du now. And because this is now in terms of u, I would like to change my limits of x to limits for u. So lower limit of u is when x equals 0, my u will be, and then you can plug that 0 here to find out what the u has to be. So that will be 0 cubed plus 1, which is 1. So this value is my lower limit for my new integral. And now let's find the upper limit for u. And when x was 2, my u becomes, so you will get 2 cubed plus 1, which is 8 plus 1, so it is 9. So my upper limit for u become 9. So no back substitution. You already changed everything in terms of u, and limits are now for u. So all I have to do is just integrate this and plug those values, and that would be u to the negative half power. When you integrate it, I'm going to gain 1 power. So negative 1/2 plus 1 is a positive 1/2, and reciprocal will be 2 times u to the positive 1/2 power, and I'm going to evaluate from 1 to 9 here. So then this is equal to, my coefficient is 2/3, and you can evaluate u to the 1/2 power is the square root of u. So square root of u from 1 to 9, and that's a 2/3 times square root of 9 minus the square root of 1, which is equal to 2/3 times 3 subtract 1. So it is 2/3 times 2, which is 4/3. Let's do a couple more practice. I have an integral of 0 to pi over 3 sine half x cosine half x. And since the derivative of sine is cosine and derivative of cosine is negative sine, it doesn't really matter which one you call it a u. But since I don't want to create negative 1 in there, I'm just gonna let my u be sine of 1/2 x. Then my du is, derivative of sine is cosine of 1/2 x. Chain rule, I gotta times by 1/2 dx. So I do have a cosine of 1/2 x dx, but I'm missing 1/2. So I'm going to create 1/2 here. I don't have a room in this problem, so let me just rewrite this. So this will become sine of 1/2 x times, I'm going to create 1/2 that wasn't there before. So I'm gonna times by 2. So 2 times 1/2 become 1. And I did have cosine of 1/2 x dx. And this integral is from 0 to pi over 3. So now I have what I need. So let's go ahead and do the substitution. So then I have 2 times sine 1/2 x is my u, and 1/2 cosine 1/2 x dx is my du. When x is 0, my u is sine of half times 0, which is sine 0, and sine 0 is 0. So my lower limit is still 0. And when x is equal, what's the upper limit for x? That's a pi over 3. My u is sine 1/2 times pi over 3, which is equal to sine of pi over 6. And sine pi over 6 is 1/2. So my upper limit became 1/2. So then this is equal to 2 times integral of u. It's a u to the first power. So it's gonna gain 1 power and then divide by 2. I get u squared over 2. And then I'm integrating from 0 to 1/2. And these 2 and 2 cancel. And I have 1/2 square minus 0 square, which is equal to 1/4. What is the integral of 1 to 5 of x squared times square root of x minus 1? So composite function is square root of x minus 1. Yes? So let u be x minus 1. Then du is just dx. But then again, I have still x squared sitting in there that I need to get rid of, right? So you're gonna go back to your u, solve for x, and then find the x squared in terms of u. So we're gonna solve this for x. You can just do that by adding 1 both sides, right? So you can see that x is equal to u plus 1. So then x squared will be u plus 1 squared. So now I'm ready to do the substitution. Integral of x squared is now u plus 1 squared, and I have a square root of u, and dx is du, so I have a du. And now remember, these are limits for x, so I need to change them to limits for u. So let's change them. When x equal, what's the lower limit of x? 1. What's u is then? You plug right there. So that will be 1 minus 1, which is 0. So that's our lower limit. And then, what was the upper limit for x? That was 5. So when x equal 5, my u become 5 minus 1. You get 4. And that will be my upper limits for u now. So no back substitution. We just do it the way it is now. So this is integral of 0 to 4. U plus 1 square, I need to multiply that out and then distribute the u to the 1/2 power. So that will be u squared plus 2u plus 1 times u to the 1/2 power du. Distribute them, I get u to the 2 plus 1/2 is 5/2 power plus 2 times u to the 1 plus 1/2 is 3/2 plus u to the 1/2 du. From 0 to 4. When you integrate u to the 5/2, I'm gonna add 1 power, which is a 7/2 reciprocal to 7 u to the 7/2 plus 2 times 3/2 plus 1 is 5/2 reciprocal 2/5 u to the 5/2 plus u to the 1/2 plus 1 is 3/2 reciprocal is 2/3 u to the 3/2 from 0 to 4. So then I get 2/7 times 4 to the 7/2 plus 4/5 4 to the 5/2 plus 2/3 times 4 to the 3/2 minus, when you plug 0 there, everything's gonna be 0. So when you use your calculator and approximate to 1 decimal place, you're gonna get about 67.5. Let's now solve a differential equation involving substitution. Solve the differential equation dy dx equal 2x times square root of quantity x squared plus 3. Recall, solving differential equation is given f prime or y prime, we are recovering what the f is or y is. So right now we're given dy dx and we would like to recover y from it. So if you're given dy dx, go ahead and multiply both sides by dx so we can have a differential form. So you're gonna multiply dx both sides. So then you will have dy is equal to 2x square root of x squared plus 3 dx. And of course, now you are going to integrate both sides. And now when you integrate 1 dy, you get y plus c. And when you integrate the right-hand side, you're gonna get a c as well. But because we're gonna get a constant on the left, constant on the right, and we want to solve y equal, and constant plus constant is going to give you all kinds of constant again. So even though you will get a constant c from both sides, we always only add one constant c. So on the left-hand side, integral of 1 dy, we're just going to say y, because we're just going to add the 1c on the right-hand side. And now here, to integrate 2x times the square root of x squared plus 3, we're going to need to use substitution, since I have a composite function. So then, of course, composite function is square root of x squared plus 3. So you're going to let your u be inner function, which is x squared plus 3. So then du is 2x dx. Perfect. I don't even have to create anything. I do have a 2x dx as my du. So this becomes integral of square root of u du, and square root of u is u to the 1/2 power du. So when you integrate u to the 1/2 power, you're gonna gain 1 power. So you get u to the 3/2 power. So we're gonna multiply by reciprocal, 2/3 u to the 3/2 power plus c. And then we do back substitution. Since this is indefinite integral, your y is equal to 2/3, and my u was x squared plus 3 to the 3/2 power plus c. So this is general solution of differential equation, and because they did not give you initial values, you will not have a particular solution. Integration with even and odd functions. And now we're going to learn some useful properties for definite integrals. So let f be integrable on the interval -a to a. If f is an even function, then integral -a to a of f of x dx is equal to twice the integral 0 to a of f of x dx. That's because just imagine you have an even function. Even functions are symmetric with respect to y-axis. Let's say this is -a to a. Because it's symmetric with respect to y-axis, when you integrate -a to a, this definite integral from -a to a will give me area. And you can see that area from 0 to a is the same as area from -a to 0, because it is symmetric with respect to y-axis. Anything that you have on the left is exactly same as anything that you have on the right along with the y-axis. So of course, if you integrate -a to a of f of x, that's the same as twice of integral from 0 to a, right? The whole thing is twice of this, correct? So that's what this is saying. Since when you plug 0, it makes your evaluation so much easier. We use this property a lot if we have an even function. This is also very useful. What is a characteristic of odd functions? As you know, odd functions are symmetric with respect to origin. So when you integrate, let's say, from -a to a, what I'm going to get is this and this. From -a to 0, this net value is negative. And from 0 to a, my net value of the integral is positive. But their absolute values are exactly the same because they're odd function. They're symmetric with respect to origin. So when you add them up, they're going to add them up to 0 because you got negative of or positive of the same value. So if f is an odd function, then integral -a to a of f of x dx is 0. Okay, So we're going to use that characteristic to look at following example. Consider f of x equal cosine of x. So this is a graph of f of x equal cosine x. And look at it. Is this cosine x even function or odd function? This is x-axis, this is y-axis. You can tell this graph is symmetric with respect to y-axis. So cosine function is even function. And then how does the area under f from negative pi over 2 to 0 compare to area 0 to pi over 2? Well, this is an even function, so area from negative pi over 2 to pi over 2 is this, and area from 0 to pi over 2 is this. So how are their area? They're the same, right? So then, how are we going to calculate integral of negative pi over 2 to pi over 2 of cosine x dx? Knowing that these two area is exactly the same, we are going to use this property and integrate instead twice the integral from 0 to pi over 2 of cosine x dx, which is equal to 2 times. What's the integral of cosine x? That is sine x. And all I have to do is to evaluate from 0 to pi over 2. So constant can be stay outside of my evaluation. So this is 2 times. You have a sine pi over 2 minus a sine 0. And sine of pi over 2 is 1. And sine of 0 is 0. So you get 2 times 1, which is 2. How about sine graph this time? Is a sine function even function or odd function? You can even see from the picture there, sine function is odd function since it's symmetric with respect to origin. How does the area under f from negative pi to 0 compare with the area from 0 to pi? So negative pi to 0, the area is negative, right? Because your y values are negative. And what is the area from 0 to pi? It is positive. But their absolute value is same. Just only signs are opposite. It's exactly same amount because it's odd function. So how does area of f from negative pi to 0 compare with the area 0 to pi? They are opposite. So therefore, what would it be negative pi to pi of sine x dx? No brainer. I'm not going to evaluate at all. Knowing that sine is an odd function, I'm just gonna say it is 0 since f is odd. And that's all you have to say for odd functions. Use the even/odd properties to simplify and evaluate the definite integral. I want to integrate negative 2 to 2, x to the 4th plus x to the 3rd plus x squared plus x. X to the 4th and x squared are even functions. And x cubed and x are odd functions. So I'm going to split this integral as a 2 of them. Rewrite this as negative 2 to 2. I'm going to collect the even functions, x to the 4th plus x squared dx. And then I'm going to separate odd functions by themselves. Negative 2 to 2, x cubed plus x dx. And because this is even, this will be same as twice from 0 to 2 of x to the 4th plus x squared dx. And because these are odd functions, when I integrate negative 2 to 2, I'm just gonna get 0. And now all I have to do is integrate that one 2 times. Integral of x to the 4th power is 1/5 x to the 5th plus, when you integrate x squared, you get 1/3 x to the 3rd power. I'm integrating from 0 to 2. So now when you plug 2 in there, I get 1/5 times 2 to the 5th plus 1/3 times 2 to the 3rd minus I'm gonna get 0 plus 0. So then this is just twice of 32 over 5 plus 8 over 3. And when you get the common denominator and calculate, you get 272 over 15. Given 0 to 5 of fx dx equal 3, evaluate if f was even function or if f was odd function. So if f is even function, let's say this is even, and you get area 0 to 5 as a positive 3. Let's say you get something like this. This is 3. Because it's even function, it will be symmetric with respect to y-axis, and you will get 3 there too. Now, if this was odd function, and 0 to 5 area was 3, then from negative 5 to 0, you're gonna get negative 3 there. Now, let's answer all this. What would it be if f was even, negative 5 to 0 of f of x dx? You see right here, right? It is 3. What is integral from negative 5 to 5 of fx dx? That will be 6, since it's twice the area of 0 to 5. What would it be? Negative 1 to 4, f of x plus 1 dx. So what's f of x plus 1? That is translating left to 1 unit. So your whole graph shift 1 unit to the left. So then you are going to get graph like 1 unit to the left, and now this will be negative 6. And the last number, this, if you go 1 unit to the left, it will be 4. But your graph stays the same. What's the midpoint of negative 6 and 4? That will be negative 6 plus 4 divided by 2, which is negative 2 over 2. So this is negative 1. So this is the midpoint of shifted graph. And they're asking what is the area from negative 1 to 4 of shifted graph. So that will be this, which is 3. And now they said, what is negative 5 to 0 of negative f of x dx? Well, when you multiply your f of x by negative 1, this is reflection about x-axis. So now the original graph looks like that, and you want to reflect that about the x-axis. So your graph is gonna look like this from negative 5 to 5. So the integral of negative f of x from negative 5 to 0 is this. And since the graph lies under the x-axis, it would be negative 3. And what would it be 0 to 5 of the negative f of x dx? I just drew negative f of x there. So if you only look at the area from 0 to 5, that will be negative 3. All right, now let's look at odd function. Integral of negative 5 to 0 of f of x dx. You can see it is negative 3. And how about negative 5 to 5? Since it's an odd function, we know net value would be 0 then. And what if you translate this left 1 unit? If you translate left 1 unit, then your graph would be 1 unit to the left, so this will be 4. 1 unit to the left, so this is negative 6. Middle is then negative 1, and your graph will be everything shifted but stays exactly the same. So it looks like that. So what will be this integral of this graph, negative 1 to 4? Yes, it stays the same, huh? It's 3. And then what do you do if you reflect this about the x-axis? So reflect this about x-axis, then now it becomes like that. This is negative 5 now, and this is a positive 5 now. So this is positive value 3, this is negative 3. So what do we want? We want integral of negative 5 to 0 of negative f of x. So that will be positive 3, since it's this. And what about 0 to 5 of negative f of x dx? That will be this, which is equal to negative 3. Alright guys, this is everything in section 4.5. So you learned a very important technique called integration by substitution. You're going to use this all the time, and I believe you're going to use this in Cal 2 as well. So please don't forget, and I will see you in chapter 5.